So, the first thing that I would like to introduce is the notion of the energy of the sequence. Okay, so the new concepts are coming. So, the energy of a sequence, of a discrete time sequence, Okay, if I have a sequence x of n, this is given by epsilon subscript x to denote what is the sequence for which you are computing the energy. This is defined as summation n equal to minus infinity to infinity x of n magnitude squared. So, basically you take each sample, take the magnitude squared and sum it from minus infinity to infinity. Now, straight away we can make an observation. Okay. Now, if it turns out that x of n is periodic, then what you will find is that as you go from minus infinity to infinity, the energy will keep on increasing and eventually it will go to infinity. So, if x of n is periodic, E of x will go to infinity. As n becomes very large, you will start to see basically this signal is not dying down and you are just squaring and adding this. So, obviously energy is not a good definition for or a good tool for periodic signals, because that will go. So, in that case what we define is the power of a discrete time sequence. Power of a discrete time sequence x of n, and we define it as p subscript x as limit k tending to infinity. Okay, just like we did the summation for energy from minus infinity, this is also, but the numerator looks like the energy term, n equal to minus k to k mod x of n squared, but you are going to scale it by the total number of terms that are there in your summation. So, 1 divided by 2k plus 1. When you go from minus k to plus k, that is a total of 2k plus 1 terms, and so the scale factor is going to be present. Okay, and particularly because if you are dealing with periodic signals and the period equal to n, for periodic signals and with period equal to n, then we do not need to look at this expression that we have. We have a good way of describing it. Px is equal to, you just have to look over it one period, 1 over n summation n is equal to 0 through n minus 1 mod x of n squared. Okay. Because as you increase more and more periods, you will basically be getting the same value again and again. So, no need to go from minus infinity to infinity, you can do this. Okay. Now, how do we relate P of x to E of x? Okay. And it is very useful for us because it gives us a very important classification of the signals that we have. Okay, so I want you to follow this part because very important, and want to look at the expressions that we have. Okay, so we will now define a new term called the partial energy. Okay, a term called partial energy. The partial energy is defined as epsilon. X is the signal for which you are calculating the partial energy, and k, where k is over a finite window, not from minus infinity to infinity. So, the partial energy is defined as a summation from n equal to minus k to k, just like the definition of the power term, but it is not, and you have mod x of n squared. Now, as k tends to infinity, you will get the full energy of the signal. This is a partial energy. If you set k tending to infinity, then you will get. So, the relationship between the power Px and the energy can be described as limit k tending to infinity, the partial energy, not the full energy, partial energy divided by 2k plus 1. Partial energy divided by 2k plus 1. Okay. Now, first thing, we have finished the definitions. So, now let us look at this. Periodic signals. Periodic signals. Okay, whether you take partial energy or full energy, you can verify that the energy value will be infinity, it will reach infinity. On the other hand, Px will be finite, and that definition is Px equal to 1 over n, the period, summation n is equal to 0 through n minus 1 mod x of n magnitude squared. Okay. Now, what is the opposite of a periodic signal? Aperiodic signal. That means it is not periodic, it is not going from minus infinity to infinity, basically it is a finite duration signal. If I have a finite duration signal, notice that basically when I take the energy will turn out to be something that is finite. Right, because I have a finite number of terms, I am taking magnitude squared, adding them up, the energy will be finite. But look at the definition of power. The definition of power is limit k tending to infinity E of x, right, the partial energy. The partial energy is a finite value divided by 2k plus 1, where k tending to infinity. So, P of x will tend to 0. Okay. So, here is the two categories of signals. One is periodic signals. Their energy is infinity, so the energy is really not useful for us. We have only the power which is useful. This is the class of signals that we call as the power signals. For these signals, we calculate the power, and that is what gives us a meaningful metric for us to understand the signal. On the other hand, if I have a finite duration signal or a signal that is decaying and is not periodic, then the energy will be finite, the power will be 0. So, this category of signals are called the energy signals. Okay. So, energy signals. So, if somebody tells you I am talking about an energy signal, then you think about a signal that is decaying and has got some sort of a finite duration that is you're dealing with. That is an energy signal. On the other hand, if somebody is saying I am talking about a power signal, then you can quickly say, okay, this is probably some periodic signal that this person is talking about. So, therefore, that is the expression that we need to think about. Now, along the same sequence, if you have a sequence, you can either talk about it in terms of the energy or in terms of power, depending upon what the characteristic may be.